is with Salesforce.com on their platform security team. So I only joined them like 6 months ago, and this presentation is supposed to be my half-year exercise of like mining Salesforce application logs and how to get into their tremendous amount of data and making sense of how their users interacting with the application and platform. And the main focus is for security threat detection. Because when I was hired as a security person on their trust team. What was a big surprise to me is Salesforce has a really big security team, more than 100 people also. So this team takes care of the entire spectrum of security, protection, defense, incident response, and enterprise security. A lot of education of Salesforce employee for secure coding type of stuff. And before Salesforce, my background has been around data mining and machine learning. My previous company is called OpenDNS. So they are this security firm started as a DNS service provider. And over there, I was doing the analysis of billions of DNS lookup records. So back then, I came out with this algorithm called secure rank. And secure rank is something really nice and simple. It's almost like the page rank. But instead of like indexing web pages, it index host names on the internet. And with analyzing the collective behavior of how people look up domains, the algorithm detects botnet command control servers. So think about it. The page rank is based on the popularity or the reputation of a web page. And this hostname ranking algorithm I came out of this looks at how malicious or malware looks at their CNC domains versus how legitimate users just doing their regular day-to-day internet browsing. So that is one. If it is interesting, I definitely like to talk more about it after this. The other project. I'm not done with talking about myself yet, but let's start. This is about statistical analysis and machine learning, but it's not so much about machine learning, but more of how I try to pull my hair to figure out how Salesforce works and how the app log data can make sense to everyone. So, okay. Other than the security type of stuff, I used to look at digital hospital data for disease outbreak detection. That was fun. And I used to model consumer shopping behavior in physical stores with RFID tracking. So that comes a little bit creepy. I've done classification for malicious web payloads, and right now I'm doing development at Salesforce. So I found this on the internet. It seems wise. So if you begin with certainties, you shall end in doubts. But if you will content to begin with doubts, then you shall end in almost certainties. I guess everyone would interpret it differently, but for me, I think this is a way people making decisions, and decision science comes from probabilistic and statistical modeling. In today's talk, I'll talk about what is the problem I'm trying to deal with, and on a very generic term, what anomaly detection is. Because most of us are not really familiar with what Salesforce is, me included. So most of the discussion will be on the general term, and at the very end, I'll use Salesforce as a case study to kind of like have a more specific idea about what the thing is about. And for our data engineer folks, there is a little bit discussion about Apache Spark, because I started using them just like half years ago, and I really like it. I just cannot stop talking about it. Okay, so the problem. I look at the security threat spectrum as this. The known knowns and the known unknowns and the unknown unknowns. I can do this all day long. So following the spectrum from left to right, we are seeing problems more difficult to measure and less controlled. And of course, you can deal with the unknown unknowns, then we are closer to deal with the most sinister adversaries, right? Known unknowns is kind of like pretty explicit, and known unknowns. This is an interesting category of threats. So most of the time, we can see certain footprints like signatures, characteristics of threats happening in the system. But as they evolve and as they update their configuration, then there are a lot of new things going on, and it's becoming a method like using volume instead of using sophistication. So these problems, correlation analysis is the most obvious method we see. And I used to come up with this investigative process called ripple effect. And basically, it is this process starting from the seeding intelligence and how you can use statistical method and use all kinds of heuristics to drive forward to find out more unknown stuff based on what you already know. Then, in this talk, the anomaly detection method I'll be discussing is to target on the unknown unknowns. And why they are important? Because they are the ones like we're most afraid of, right? We don't know in what time and in what form this attack would be happening. And so for these attacks, what are the methods we're left with? Anyone care to just throw in a few thoughts or?
Can you repeat the question?
To detect unknown type of attacks, what are the methods, like in a generic term, like we are left with? Thanks.
Now we
Thanks.
behavior-based analysis. Yeah.
Exactly. Actually, those are the things I'll be talking about like in a little bit. So we're at the situation where the phishing email has been clicked and the malware has been executed, and the user's credentials has been compromised. So whoever either the attacker itself or the malware is already in the system and they are doing things in stealth mode, like we don't know they are happening. Okay, so that is one of the perspective defining the problem we're trying to deal with, and the other perspective is in this application world, we are seeing our detection or attack services basically fall into these three big categories: infrastructure, endpoints, and cloud platforms. And apparently, there are more and more cloud companies, and Salesforce being one of them. So the security of a cloud platform is becoming more and more critical. And system being compromised, it is not really an assumption. It's more of a reality now. All right, so this is a solution I cannot come up with. It's like, how do we deal with the unknowns? And we formulate the solution to be a combination of anomaly detection, behavior modeling, statistical analysis, and unsupervised learning. Why unsupervised learning? If you are familiar with the machine learning terms, unsupervised learning versus supervised learning, the difference is if we have the ground truth, do we know what is what? For one quick example, is like, okay, for supervised learning, you can give the machine a list of characteristics of people being Chinese versus Russian. It can be the eye color, hair color, height, and then the machine will kind of like figure it out. Oh, now I know, like, hey, she's a Chinese based on all the characteristics the machine is observing. But unsupervised learning is something we don't have such labeled data. We don't have anything to tell the machine, okay, this is something you should be looking for, and if you found this, it will be a cat or a dog. And why behavior modeling? It's because think of this as the dynamic analysis for malware sandboxing. So you'll be observing the malware doing all kinds of different stuff. And in the cloud platform or application circumstances, you're seeing users interacting with the platform, using the app. They doing their day-to-day work, executing their workflow in the system, while the malware will be doing similar but subtly different things. So this is the behavior we're trying to model, trying to observe, and we want to apply statistical modeling and anomaly detection type of techniques to make the machine realize, oh, this is something bad, this is something we should stop here and take a closer look at it. And how is this all possible? We have all the algorithms developed, technique developed, but the single most important thing is the Haystack. So we are kind of happy that we have this Haystack to start with, right? That is only made available because of all the computer resources dedicated to logging, right? Now we get to see everything happening in the system, and the question becomes, how do we make sense of this? And Haystack's like, oh my God, I don't know people like me. All right, so a little bit real kind of like examples of this Haystack, like what are the advanced data look like in a Salesforce type of platform. We have entities, we have users, we have organizations, and we have systems, we have machines doing all kinds of activities, and for the metadata of these entities falling into big categories in terms of the idea of them, the IP addresses or timestamps. And there will be a bunch of information we derive from these metadata. Well, who's this user? Is he on the Salesforce? Is he on the sales team or marketing team, or this is a hiring manager? And from IP addresses, we can infer what country is this, or to the geocity location. And the most interesting part is the behavior. So the interaction and the actions users and systems interact with the application. So the user log in, authenticate himself, and the user start looking at a bunch of pages, maybe catch up with a sales lead he's following, and then pull out all the contacts he has and trying to figure out who should I annoy today. Then he will probably update a few records regarding, okay, this case has been at this phase and already got down payment for this. And he might be doing password reset because he cannot remember. So now, after a big look at what a Haystack is, I want to talk about the challenges. Why? Because if I don't talk about them, then you'll be like, oh yeah, this method, there will be tons of challenges of them. So the first one, obviously, what we're dealing with is a rare event detection problem, and it is rare event detection. So all the things we're trying to detect, they are in really small odds. That's a good thing, right? Consider the extreme, which is the terrorism detection. How do you really detect a terrorist attack happening? From all the data, all the things happening in the world, all these events can be simply considered statistical noise. Most of the sampling methods and whatever smart methods being using in the statistical world, they will be useless because we cannot do a lot of things there, right? Sampling is one of them. If we do sampling, then it's obviously can we sample the right stuff. At the same time, whatever models or whatever behavior methods we built up, there's a chance, this is a game theory, there's a chance the attackers will be smart enough to adapt to the system and try to beat the behavior model. Try to behave not as anomalous as you might think. And also, I probably don't want to mention what is the size of the Salesforce app log and what is the event rate per second. But you feel free to take a guess. So, with such a big data, here comes big mistakes, right? We are blessed because the data storage or distributed computing technologies has allowed us to really calculate things on such a scale. But at the same time, what is a robust enough error rate? Okay, let's say 0.001%. It is pretty low error rate. Regardless what classification models you have seen or whatever machine or data-driven kind of models you have had played with, 0.001%, it is a really low error rate. But here's the thing. We have a few billions of things we have to making detection upon. And this 0.001% times a billion, then it becomes a pretty big false positive pool. So how do we deal with that? some difficult, some more technical problems introduced by distributed computing here. Correlation is hard, and because of how the data is organized in the distributed system, ordering is hard. So how can we be smart about that? All that said, I want to show this picture because I learned this use case from a presentation by a Berkeley professor who's in astronomy. So this is a picture from that presentation, and for anyone can guess what this is about?
Is it a comet?
Not a comet. It looks like a comet for sure. And the code is I don't read how the X600 code thing. This is part of the galaxy for sure, and this little thing, the little blue dot pointing out there, that is a supernova. So what the professor and his colleagues did is they have this giant super telescope. I don't know, maybe there's a name for it. So they have this giant telescope there and scanning the universe or part of the universe day and night, and they are collecting a few billion of data points a day and coming up to total 20 terabytes of data a day. So all the movement, all the color, all the diameter, all kinds of different characteristics they can think of to model I don't want to call it a star, but the objects in the universe. And with all this data, they use an anomaly detection approach to detect this supernova being formed 10 hours before it comes to real detection by the normal regular method. So what I'm trying to say here is this is a really small rare event, and what people have done there has been really inspiring. And why we cannot do something like that? So the real opportunity lies in today we have this gigantic logging infrastructure, and we can decide what we want to log about the system. So we keep track of every single footprint of what's happening here. And at the end of the day, our approach or our system should be able to make a good sense of all these data. All right, so what about the method? Anomaly detection, that's really think about what is anomaly. This photo is 2x2, a two-dimension space, and each of the individual case is just symbolized as a round dot. We can call out the one in the red circle as anomaly, but what about this little thing in the green circle? Is this anomaly or not? So it almost becomes a philosophical question. How do we determine anomaly? And statistically, most often we formulate this as bounded by the error rate. How many errors can you afford to pick up things as anomaly? And with Salesforce as an example, a few heuristic scenarios, what an anomaly behavior we can see from a user. So is a user stepping through a multi-step business process in the wrong order? That means we have to have a way to model the order, the sequence of such behavior. And does this user access things like with insufficient permissions? Then we have to have this data model to record every object and every user and their permission sets mapping. Is the user exceeding his individual user-specific action threshold? That means, do we have a threshold to impose on each user and what the threshold should be? And is the user seen from two IP addresses concurrently? Of course, that happens quite often, more often than you can imagine. There's all kinds of like different scenarios. People are doing this. One scenario can be their cookie has been stolen and used by a attacker, or this user is sharing his cookie on purpose, so they don't need to buy multiple licenses for their organization. Well, if we get into data mining type of terms, the anomaly detection methods normally map into two big categories. And one is distance-based. And a bunch of algorithms there, nearest neighbor SVM, single class SVM, or unsupervised random forest. So there are a lot of choices. But it all depends on how we want to model this problem. What about the sequence of these behaviors? So the other category is the sequence-based anomaly detection. And this concerns with we can call it a path a user towards when it interacts with the application. And there is a probability associated with each of the paths. So a lower probability versus a higher probability, are they considered anomaly versus a normality? So when I think of this, I just imagine there is a two-dimension space, and one dimension is the billion of users, or even tens of millions of users, and the other dimension is time. So as time evolves, the user will come to this point to do such a thing, and at another data point, time point, this user will do something subsequently. So with a sequence-based method, we'll be able to capture this user from his own history to the current state of this user. And this user can be considered anomalous if he's behaving really different from himself, or look at when we take a snapshot of the two-dimensional space, we'll be looking at millions of users. And among these millions of users, we'll be seeing this 100 or thousands of users. They are behaving really different from the rest of the group. So at the end of the day, the solution is supposed to be the combination of both of those two categories of methods. And a little bit high-level design of the detection system. I call it profiling-based adaptive signaling. So this takes care of the history part. This is supposed to capture the how a user's current behavior deviates from its previous behavior. So all the history, all the things has been logged in the system, and we'll have to go into the phase where we model such patterns and profile these users and define the normality of this user and come to this data abstraction called profiles. Then as we observe current actions of a user, our detection engine will come into play. So look into a bit detail about this detection engine, threat seeker.
we are processing these logs either in batch or in a streaming mode. Basically, we're observing everything happening in the system. And they extract interesting events here. We call it SE events, which is a sensitive action event. So in terms of behavior, we have the simplest rationale. Basically, the attacker, whatever they do in the system, they try to get something and they want to turn it into profit, into monetary value. So most of their actions will be something more or less falling into creating admins, resetting passwords, or exporting data, exporting sales contacts, things like or things similar. And we have a bunch of behavior to signal translation engines that translate the action data into different signals. And these signals would have a more concise indication of whether this user is doing something just legitimate or malicious. Some example of these translating this behavior into signal. So there are rate analysis. So how often this user making such a call and how often this user invokes this API calls. And there's such analysis. So a lot of times we are seeing concurrent behavior from multiple IP addresses and from multiple countries across the continent. So is it a session hijacking type of attack? And the other part will be the geolocation analysis. And essentially, sensitive action is the other category we monitor very closely. Also, the high-frequency API calls. So that is a very high-level design of this detection method. And why this method is valid or useful? First of all, we are dealing with the unknown unknowns. So we have to make sure that our method requires minimum to none per knowledge of these attack patterns. As we are building the profiles and monitor a user's history closely, these models are supposed to be adaptive to user behavior changes. So normal users do all kinds of weird things, right? If the system is static, if it doesn't adapt to all these legitimate changes, then the system will be pretty much useless because it's detecting so much like nonsense stuff. At last, methods should be addressing various level of user behavior volatility because different users, their behavior changes will not be uniform among themselves. Some users will be more predictable other than the rest of them. So the notation for to model such various level of behavior changes, we use entropy. For example, we see some users coming to a bunch of different IP addresses, but they do this day in and day out. In the past 3 months, they've been doing this. So this would be less of a signal compared to a user who has been coming from a single or just a couple of IP addresses in the past. But all of a sudden, this user account has been accessed from tens or hundreds of countries or IP addresses. All right, now come to the part of Spark. So all this is only possible because of the big data technologies. And at OpenDS, I've been dealing with small data like in the most part of my life. And only after I joined OpenDS, that is where I started picking up all the big data technology. Hadoop, Pig, Hive, and a bunch of other geeky terms, as we call it. This is the most recent stack like I'll be using. So we have this event selection and management part, and for data storage we have this Hadoop part. And Apache Spark is a in-memory computing engine, which turned out to be really fast and efficient, and the whole technology package supports machine learning, all kinds of statistical modeling technique. And it has a nice interface with Python. Spark is native in Scala, but since I'm a Python person, so I'll be using PySpark. And to complete this picture, of course, the detection has to be fed into a response and feedback loop. So it's not supposed to be a Spark tutorial, but I think my little experience about Spark, using Spark in this application may be useful to some of you. So Apache Spark is something you should, once you get your hands on, you can just pretty much forget about Hadoop and MapReduce. The speed or the efficiency wise, the comparison can be seen in the little histogram. And it supports a complete package of different libraries, Spark SQL streaming and machine learning, and also has a graph analytics computing engine. And how easy is it to use? So if you are a Python person, then to start translate your Python object into Spark is as simple as just use this Spark context as c.parallelize. So basically, your Python object will be becoming a resilient distributed dataset. It's RDD. And it can be spread across multiple data nodes. And vice versa, you can translate a Spark dataset into a Python object just using the simple function called .collect. In PySpark, the mapping or transforming function call is the .map function. And you can also do group by keys or reduce by keys fairly easily. And this paired RDB is a pretty important concept. Paired RDB use this key value pair to represent your data, and you can easily to group on the keys and reduce by the keys and to get the aggregated statistics you want. Okay, just a little bit more about PySpark. For people with experience of Pig or Hive, normally the user-defined function is the customized logic you want to implement, but with a lot of difficulty. But in PySpark, such user-defined functions can be simply implemented in Spark in Python, and such functions can be called in PySpark environment, just with one statement. All right, so this is almost the end of the discussion. A quick case study. So how does Salesforce app work? It took me 6 months to sort of make sense how it works and what are the log data is constantly speaking out. So the font size kind of scales to the amount of work I've been doing. One unreadable picture of the Salesforce, the sales apps workflow. That's how a salesperson generates a report and manage contacts and update opportunity, etc., etc. So with this picture, I just want to give you an idea, like what is the complexity of the data, and at the same time, the richness of the app log, how we can capture the entire workflow of each user. At the same time, this picture shows you, wow, how do we kind of model such a behavior? Now I'm using the same slide of the ad events data. What are they? The main categories of them. And the example detection model here includes a few signals, including the positive signals versus the negative signal. So positive signal, I've covered most of them. So what if we are seeing this new IP, and what if we are seeing this user coming from multiple countries at the same time? Or what if we are seeing this user doing something really different from his past behavior? And what if this user has a really short interval between his login versus start downloading data, start exporting reports or contacts into out of the platform? Or are we seeing like very multiple user agents in the concurrent session? And there are also negative signals. Those are the ones that we use to indicate like this user is more likely to be a legitimate user versus a hacker. And at the end of the day, we'll need a smart way to combine all the signals and do a stack ranking to generate this list of events that we find we need to further investigate. For stack ranking algorithm, there is a number of choices: numeric approaches, or unsupervised learning, or backpropagation approach, or even stochastic modeling. So at the end of the day, we want to optimize the system to detect the most positive cases that minimize the number of errors. So that's about it. That's the framework, and that is a prototype. And there are a lot of opportunities here. So we always keep these question marks in mind when we develop anything in this direction. So we conserve as false alarms, and can our method deal with man in the middle, man in the browser, and what about new users? What about users with behavior haven't started modeling? Also, what about multiple stage attacks? And the last question is, when I was at the Berkeley's professor presentation, asking, so with this 20 terabytes of data, with this billions of stars in the sky when you're trying to observe and discover new things, how many false positives, how many cases like you discover a day that turn out to be false? So his answer is like 30. Well, 30 is how to say, is it a good number? We don't know. But think about it. This supernova detection only happens once a few years. So you be spending your life dealing with the 30 false cases on a daily basis. Then is it worth it? Well, my take is as Amazon started doing recommendation 15 years ago, we just find it like so quirky and so annoying. But nowadays, it's like recommendation is pretty much part of our life. It's on LinkedIn and it's on Twitter and it's on Google search pages. So we still find it annoying, but it sometimes turns out to be useful or less quirky. So I think all the things take patience, but at the end of the day, I think it's worth it. And that's all. I only have questions.
Can you go back to your high level? Here you show the profile of the builder and the profiles to fit into the signal logic. Is there something that goes without the loop? So based on what you learned from your logs and analysis that you do you build a profile, or is that a completely separate process that you do?
We don't have the loop right now, but feedback loop is such an important concept here. It's like when we do the detection every day, then a lot of times we'll keep detecting the same scenario just because it's so weird. And if we don't take it back into the loop and incorporate it somewhere upstream of the detection chain, then we'll be making the same mistake over and over. So that's definitely a critical and necessary loop up there.
Yeah, it seems to me it might be related to that 30 false positives that astronomer must do. Because if they could analyze why it false positives, feed that back in, it would lower it.
I didn't have that follow-up question for him, but what I would imagine is they will take this back into their training set and probably label this as, you know what, this is a false positive and do not classify it again. But even with that, we'll be still seeing new weird things and making new mistakes. So, please.
So are you applying protection to Salesforce now? I mean, you're detecting these anomalies. Are you now enabling protection for your data and based on what's maybe a high threat ranker score you might see in these anomalies?
We are, but it is a back-end implementation right now, so this is not a feature in the product itself. We have this at back-end, and we are generating, detection results, but all this is not visible to anyone who's using Salesforce because this system is still being improved and further tested.
How often do you have to retrain the kernel?
That's a good question. This depends. For our testing so far, we have to retrain it on a daily basis, but in the long run, we want to have this more of like a online learning thing. So is it like gonna be per minute or per event retraining? So that is the ultimate goal we're trying to find.
I can take a quick one. So, you guys try to have like smaller funnels or, let's say, you can do maybe like AppSec of like, so the problem is that the user agent is like whatever you're looking at. So if you have a AppSec one funnel, have like 80 people on the page, stops or something.
As I understand, you're asking like, okay, can we look at this as like a collection of mini classifier, and each individual classifier will be trained on a different time scale or a different set of data. And, yes, that is not something happening right now, but that is definitely the way to go, okay? Because considering a different perspective of behavior, each mini classifier will be monolith, and some behavior will change more often than the rest of them. So, yeah. All right, I think my time's up. Thank you everyone for coming to my talk. Like, all the beautiful morning is sitting on the top, and the beach is right over there. Thanks.
You had a lot of good ideas for what we want to eventually
Everything is in English.
but
I want to make sure you get
I don't know, after half an hour, I wish I had an idea, so I guess it's really tough.
leaving aside entirely from all that.
From AJ for that. Really? How long that one? Let's